Assalamualaikum. Dr. Imran, kindly unmute yourself. Dr. Imran.
Anyways, I repeat again. Okay. Okay, in the Sara Faridi's lecture, she explained that regarding to every monomial ideal, you can always associate a simplicial complex. And this simplicial complex is special in the context that you label the vertices of the simplicial complex through the monomials, which are appearing in the minimal generating set of this particular ideal. And there are two simplicial complexes, two complexes of this simplicial complex she discussed. One is the complex she called Taylor resolution, or another word, Taylor complex, which gives some Betti numbers. And similarly, another one is the scarf complex. And regarding to the monomial ideal, in algebra side, we have the minimal free resolution. She introduced a definition of minimal free resolution. And regarding to the minimal free resolution, we have the Betti numbers. So the main thing, the main very well-known result is that this Betti number of the ideal is bounded above by the Betti numbers coming through the Taylor complex of this simplicial complex. I should better to use the word Taylor complex. And it was already scarf complex. And the scarf complex is giving me this Betti number, and this is the lower bound of the Betti number, what we obtained from the minimal free resolution of the ideal I. Okay, the problem what she mentioned in, okay, probably you need this thing. I try to be on this side so that everyone can note down the standard references. Oh. So standard references for the study of this kind of keyword was the topological methods by Bonjour, not Bonjour, Bonor, whatever. Bonner. And then the second important reference was algebraic combinatorics by Welker, Ulrich and Welker. And the third important reference was organized collapse, an introduction to discrete Morse theory. And this was by N. Kozolov. Okay, the major interest or the major problem is that for any given monomial ideal with okay, now discussing the classes of the monomial ideal, one has to pick a particular invariant. And what Sara discussed, Sara classify the monomial ideal through the projective dimension. So she mentioned one of her results that in the case of projective dimension of the monomial ideal 1, okay, the major question is that in this particular context that can we obtain the minimal free resolution of the ideal through either the Taylor complex or the scarf complex. So you can see the Betti number, scarf complex is too small and Taylor complex is too big. But is there some, okay, there is the interest in studying that the relation between the measurement, how far is the Taylor complex is from the minimal free resolution. So that was one of the problem is for a particular class of monomial ideals determine in other words, determine the gap between the Betti numbers. Okay. So the exact, you can say the relation between the Betti number, something subtracted. So Betti number you are obtaining from the Taylor complex minus something. So that is something, a problem. One can pick any class of monomial ideal and determine that how far is the Taylor complex from being short, being the minimal one. And another problem which is of the interest of a similar kind of nature, determine the classes of monomial ideal for which the scarf complex of this one is the same as the Taylor complex of this one. This is another problem which was described by Sarah. And one standard reference for the study she mentioned is that in order to address this kind of questions, the best way, because just to remind, whenever you are studying the free resolution, so the things are going something like that. And the maximum, for instance, this is the level 0, then so on. Say this is the level D, the maximum level, say A0, AD. So this particular maximal possible length of minimal free resolution, we call it the projective dimension of I. So according to Sarah, a good attacking point is to keep this, if this complex smaller. So what she studied with one of her master student, Ben Hersey, is for this case, for the ideal having the projective dimension only 1. So that is the work which was done by Sarah with Ben Hersey, where they give, because in that particular case, they give combinatorial condition that under which condition these complexes, the topological complex, the topological, so Taylor complex and scarf complex are giving us the free resolution of this monomial ideal. So this is one problem. And in the case of projective dimension 2, so in other words, in projective dimension 1, they determine the condition on the ideal under which one can determine the Betti numbers through the Taylor complex or the scarf complex of the simplicial complex delta M. But for projected dimension 2, there are some counterexample, but again, one can devise certain condition. And for projected dimension 2, it is open. And 2, 3, and higher cases, it is widely open. And the good reference is this particular paper of Sara Faridi with Ben Herzer. And this is a thesis which can be found on the Google too. Okay, that's it regarding to Sara's project. Anyone has any other project what was described by Sara? In addition to this one, they can add on. Okay, if this is the case, now let me just open up the projects by Taiha. Let me just tell you that this containment problem, that was all about the containment. Containment problem is one of the central problems in the area of commutative algebra and algebraic geometry. And Taiha was discussing about various conjectures. So one of those conjectures was the de Mailly's conjecture, in which he was discussing about the bound of Waldschmidt constant and t plus n minus 1, where this is a Waldschmidt constant. And this is defined as limit m approaches to infinity alpha of I m and m. Now, what is alpha of an ideal? Alpha of an ideal is the minimum of the degree of the U such that U belongs to I. So this is the minimal degree of, if in the case of monomial ideal, so this is the minimal degree of the monomial appearing in the generating set of the ideal I. Okay, the central problem, what is the containment problem? The central problem is basically determine, I'm sorry, I will get aside a bit. Okay, determine M and R such that the symbolic power of M is contained in IR, where R, the ring underlying is usually the polynomial ring over C, because this problem is in algebraic geometry, and I is an ideal. So symbolic power of M. Okay, so Taiha gave a technical definition which is there in algebraic geometry, but I will define it in an easier way. So regarding to every ideal, we have the primary decomposition in this way. So every ideal has a primary decomposition. So symbolic power of I, if I take the symbolic power of I, so this is nothing just the ordinary power of each of its primary component. So this is the way the things can be viewed through algebraic geometry and in commutative algebra as well. So there were many conjectures. There were one is this conjecture, then there was another conjecture, which was stable containment. And there are some inequalities he was furnishing that which were known for particular cases, particularly in the projective spaces when he was using the scheme, Hilbert scheme. So IR for R, very, very large. And this is a kind of stable containment, which simply implies the de Milly's conjecture and these kind of problem. Okay, what are the possible open problem is to refine these kind of inequalities. So what we are obtaining, and the main thing which is of interest is let I be a radical. In other words, find the class of ideal, particularly the radical ideal, radical and homogeneous. That ideal in R of big height H. So let me just tell you what is the big height. So we have a primary decomposition of the ideal. So in the primary component, the one which is having the biggest height, we call it the big height of the ideal. With big height H, does the containment one. Okay, a good reference to start this particular project is the survey by Taiha, which is available on arXiv on the containment problem. And in that particular survey, he gave a comprehensive detail of all the containment what he was discussing in his lecture. The second thing, because the containment problem is not so straightforward, so it is studied. This is something which was not discussed in his lecture, but this is of the interest from where the birth of the Waldschmidt constant appeared in the literature. It is the resurgence of the ideal. Resurgence of the ideal is defined like this. Rho of A is the supremum of MR, quotient R, such that IM does not contain in IR. So you can see that it is a kind of the maximality of M or R where the containment problem does not hold. And bounding the resurgence, that means beyond this particular point, the containment hold. So finding the resurgence is very difficult problem. And the bound of the resurgence, the bound of this resurgence is basically, that is a strict bound, is the Waldschmidt constant. And there is a lot of interest in bounding the resurgence too in the literature. And there is a paper, very unusual paper, in the context of algebra, commutative algebra. The title of the paper is the Waldschmidt constant Waldschmidt constant for carefree monomial ideals. Okay, you can see that this is a very, very particular case and which seemingly quite simple. And this is the paper which appeared, I think, in the year around 2015 or so. So these are the authors. So you already have seen these names in Taiha's talk. Sean Cooper, Lisa Goloado. Harborn. Almost all the big name of this area. Jensen. Nigel. Then Secolano. Then Eventual. And then Wu. So there are too many authors of this particular paper. Okay, this paper is very, very important in the context of the last question I asked to Professor Ha. In this particular paper, they have given, they have described combinatorial and algebraic and computational. Ways of computing Wald-Schmidt constant. There is an interest of building the algorithm, again, particularly the students who are in IBA Karachi. So I do understand that Junaid and his team is more interested on the problem which are of the computational nature. So there is a lot of interest in finding algorithm which can determine the Wald-Schmidt constant. And in this particular paper, you will find some of the algorithms too. And they use linear programming to compute the Wald-Schmidt constant in the computational point of view. So there is an interest. You can pick that particular algorithm and you can find some more fast algorithm or smarter algorithm, smarter ways of computing Wald-Schmidt constant quite independently. The second thing, what is important regarding to the combinatorial point of view, I would like to mention one of the result of this paper, which is worth mentioning here, so that you get an idea what they have proved. Let me just tell you, this is quite unusual in the area of commutative algebra, algebraic geometry, a paper with too many authors.
These are all
the author of one paper. And almost they are the leading names in the area of containment problems. So there is a theorem in that paper, and the number is 5.3 in that paper. And the result is this: let I be a square-free monomial ideal with the big height of I is equal to E, then the Wald-Schmidt constant of this carefree ideal is bounded by, again, this is a really, really difficult problem to give the exact value of the Wald-Schmidt constant, because if you see the definition of the Wald-Schmidt constant, where I have mentioned the definition. Where's the definition? Okay. Yeah, here it is. This was proven by Mitchell Wald-Schmidt himself that this limit always exists. This limit for a homogeneous ideal, this always exists. And if you see, the computing is already quite asymptotic. So computing of alpha of I of m is not so simple. And even what they have given in this paper is the bound of the Wald-Schmidt constant. And this is bounded by alpha of I plus E minus 1 and E. And my question to Taiha toward the end of his lecture is that this is quite surprising that since this paper appeared, definitely there are some interests there, but what can be done? You can pick any class of graphs or simplicial complexes. You can pick any of these two and find the bound of the Waldschmidt constant determine the bounds of this Waldschmidt constant. And again, according to Taiha, this bound may get refined in particular cases. There is an interest. Refined bounds in particular cases. Okay, this is a little bit tough ask, but again doable. One can apply the combinatorial method to compute the Waldschmidt constant. And in the same paper, they have discussed the combinatorial ways of computing the Waldschmidt constant. Then another task what Taiha suggests regarding to the same problem is that, okay, by using the same theorem, you can pick the class of the ideal which is coming through the graph or simplicial complexes, use this particular theorem and finding the bound for the combinatorial bound of the Waldschmidt constant, probably by using the same theorem. And I think this is the good starting point. You apply the same theorem and you see how the bound is changing. And then combinatorically, you can evaluate the cases or certain cases where you can think you can be lucky in finding the equalities. But this is also very interesting to look for the equality, maybe in very small cases where this bound is sharp. So in other words, determine the cases for which you get equality. Okay, these are the projects which were mentioned by Taiha, but there were too many conjectures which he described, which were very complicated one. But definitely all of those were related to this inequality, and he was keep on refining those. So you can get further detail from his notes. And then, okay, Sara Faridi done. Then we have done with Taiha. Yeah.
I have a general question about the resurgence of the ideals. Usually the ideals in resurgence are considered to be the homogeneous ideals with the ordinary problems.
Yeah.
So is that possible in case of the non-homogeneous ideals?
No, yeah, this container problem is only for the homogeneous ideal.
So we cannot do it for the non-homogeneous ones.
This problem is particularly for homogeneous cases. Okay, and all the monomial ideals are homogeneous one. So in any case, okay, this is quite interesting. They have this paper for the scale-free monomial ideal case. Still, nothing is known for monomial ideal. Again, for monomial ideal cases, the things are widely open for general monomial ideal. So again, this is a problem which has combinatorial roots, and one can try by looking at. We don't find anything regarding to resurgence which are coming from maybe simplicial resolution or any resolution of the ideal or the Betti number. Nothing is related. Let me just tell you the bound, everything is quite clear. So E is the big height, which is not difficult to compute. alpha of I is the minimal degree of the generating set, generating monomials of the ideal. So these things are very easily deterministic, but yet bounding the Waldschmidt constant, and definitely this is the upper bound of resurgence, which below which you never get the containment holds. So that is the other way to study the containment, the other side of it. Okay, then regarding to
Tropical geometry में कुछ पता है?
ट्रॉपिकल ज्योमेट्री का शाहीन बताएंगे, वो पेज उधर पड़े हैं,
ये?
वो पड़ा है वो।
Classical problem.
या ट्रॉपिकल ज्योमेट्री के मैं सिर्फ ये बता दूं कि Hannah was discussing about NDG, determining this thing for the curve with genus 1, right? And the problem is widely open for genus 2 and higher cases. So I think she was very quick in telling the problem. So she computed in her lecture for genus 1 curve determining all NDG, the number, but the problem is open for the curve when genus is equal to 2 or above. Regarding to hope, any question from Karachi, IBA Karachi? Okay. Okay. Hope was discussing about, he introduced an interesting setup. Again, he was also discussing the symbolic power of the ideal, and particularly in the monomial case. Regarding to every ideal, we have the structure of the restring. And regarding to any ideal, so I denote it like restring of ideal I. And then regarding to, this is the standard setting. So we have an ideal, we have the restring of the ideal, we have the power, ordinary power of ideal. There is already interest in studying the depth of R quotient IM. So particularly the work of Chung, Herzog, Hua, and these persons have a lot of results in this particular direction, where they discuss the behavior of the depth function when you keep on increasing the power. Okay, what was new? What Hope presented in his lecture is that discussing the same problem, but instead of taking the ordinary power, let's take the symbolic power. And then they constructed the Riesz algebra. So Riesz algebra is something, I'm not sure whether I'm correct, please correct me. In this way, and when we construct the Riesz algebra with respect to the symbolic power, yeah, I think R is there, I square R is there, and then so on. And this is, yeah, this is K. And in this case, the same thing, I with R, not, okay, single R. Then I square, instead of I square, we have the symbolic power. So this is the analog structure, what he built. And then the main question which of interest is exploring exploring the relation. Okay, exploring the relation between depth of RIM and depth of R. This problem is widely open. Nothing is known in this direction. So the relationship between, because this is a Meyer, this is also a Meyer, but nothing is known in this particular direction. Where neither this way, nor this way, neither equality. So again, this would be an interest to look for the cases where you can establish one of these relations. Okay, other than that, there is a result by Herzog, Libby, and Chung, which says that the depth of symbolic power of T is eventually periodic, and Hua with Invari prove that when I is square-free, monomial ideal, particularly when we are talking about the square-free monomial ideal, and there exists, okay, then the limit exists, this particular limit of the depth of R I T, symbolic power of T, is equal to 0. So these are some latest finding in this particular direction. So basically the whole stuff is about exploring this particular structure. And the problem which he stated toward the end of his lecture is that like depth, there is another invariant, which is the regularity of the ideal. So we don't know the behavior of the regularity of IT. One guess is, again, the things are coming from, because there is an analog structure. So if something holds here, people start with trying to find a similar kind of results here. And again, regarding to regularity, we know that regularity is a linear function when t approaches to infinity in general setting, but nothing is known in this direction. So nothing is known for the regularity. And again, determine the cases when R our IT is periodic, if I is not a monomial ideal. You can see the result of Herzog. This is only for monomial ideal. So when the ideal is not monomial, we have no idea. Nothing is known in this direction too. So this is regarding to Hope. Taiha, Hope, Sarah Faridi, something Hana, and the rest of the lectures are on the way. Shaheen already explained her problem. In addition to that, if someone has any projects, so they can come up. Over to now Hassan. कोई और है?
I work in Lee algebra. I think that's quite. I mean, of course I can. Should I? But पता नहीं कितने लोगों को Lee algebra की definition भी पता है क्या?
Yeah. Azhar Farooq hai. Oh.
Okay, any problem?
Okay,
Any
the general
participant?
problem is to, Lee developed a theory of, his theory of Lee algebras comes from understanding differential equations. So he proved that if you take an ODE of order greater than equal to 2, then the corresponding symmetry algebra is finite dimension.
Mhm.
And it's a algebra which has to fields in R2. And then he went on to classify all subalgebras of vector field, finite dimension subalgebras of R2, and he determined the corresponding differential equation. So the natural problem is to ask yourself what happens when you look at vector fields in R3. And the starting point would be what are the nilpotent ones for it. Even that is not true.
That is not.
That is also not true. So, and then find the corresponding invariant equations. This one has to, if you had asked me to prepare some lectures, then I would have done it, but that's completely different from commutative algebra.
Yeah. Okay, I tried to put as many things as I could from the lectures. Definitely, some of you already had some discussion with Sarah, and you have seen these lecture notes. So all the lecture resources, everything which was mentioned by the speaker, they are there already on the website. So let me just tell you, none of these problems are undoable. All of them are doable one. So you need to just pick one of these two, and you can work in for simple examples. And this is a starting point. And from moving from the example, you start looking at something will be coming in your way. So this is the way, this is the attitude you can
No, I
move.
think if you pick up any recent paper and start
Yeah,
reading it, you'll see some
yeah.
things which is understand and try to understand and all those things.
I think if there is no other point, then we can stop here. Junaid, are you there?
So let's give Imran.
We need a confirmation from all the speaker that I described it well. I hope.
Well, you have recorded it, so they will get that.
Yeah. Okay, all the recording and everything will be available on the web page.